In AT85, there are 11 instructions who work with the stack. We already worked with one of them or know one of them, which is LXI, SP, and double. We saw this in the transfer instruction sections, and we said that we have four types of this kind of instructions that we mentioned: a register pair and a double byte, right? Like LXI B, C, sorry, B, D, H, and SP. B would be the double, would go to the BC register pair, or D register pair, or HL or SP register pair. And the way that it works is that the programmer would provide the double byte or the 16 bits that it wants to send to the register pair immediately, and the opcode was 00XX001, which makes this instruction with the opcode of 01 in hex, 1121 and 31, which 31 would be this one, which is move or load some immediate value, or not some. X would mean 16 bits, would provide 16 bits of immediate value inside the SP register pair. And at the memory value, first it would have the opcode and then 2 bytes. At the assembly level, it would be LXI, SP, and 1122. In the memory, it would be the opcode of LXI, which is 31, or LXI SP, which would be 31. And then a lower byte comes at the lower address, and higher byte at the higher address. Here would go towards the higher addresses. So this was the first instruction, which involves the stack. Then we have for push, for pop, and these two other instructions as well. First, we want to work with the push instructions. Unlike what we explained in the previous lecture, we said that push could have an argument. This argument could be immediate byte or a register with the length of 8 bits. While in AT85, the argument is always a register pair, and therefore the length would be 16 bits or 2 bytes of data. We only have these four types of push instructions: push BC register pair, DE register pair, HL, and PSW. PSW means that the register pair is A and F. A would be the A register, F would be the flags register. So flags register would act as the lower byte of these 16 bits of data. You can't push immediate value in AT85. The argument or what you want to push to the memory should always be a register pair. So you need to first move your value in the register pair and then use the push. Also, this is the opcode. Therefore, the opcode for push B would be, well, 0, 0, 0, 1, 1, 0, and 1, 1 would be the XX of all of them. Then the rest would be the same. 1 1 0 1 0 1 1 1 0 1 0 1 1 1 0 1 0 1, making this C5, this one as D5, E5, and F5 as the opcode for all of our push instructions. Now let's see how this push B would work. The first thing that would be done is that SP, you see in here the length of the argument was one byte, therefore the SP would be decremented by 1, and then whatever the argument was would be moved to the memory location that SP is pointing to. Here again, SP is first decremented by 1, then whatever the argument is, the higher byte of the register pair would be moved to a memory location that SP is currently pointing at. Then SP would be decremented again, and this time whatever the lower byte of the register pair is pointing to, whatever the lower byte of the register pair is, would go to the whatever SP is currently pointing to in the memory. Now, as we said, if you have a BC register pair, B is higher byte, C is lower byte, right? C, the lower byte should go to the lower address, and higher byte should go to the higher address. Based on the way that a stack would work and this decrementing thing, it means that B would go to the higher byte and C would go to the higher address and lower address. Now let me actually completely show this and present this, that how the memory and CPU would work together for the push B instruction to get executed. And also you might know that the instruction length would also be 1 byte, because we don't need to provide any data or any address, unlike here in our imaginary CPU that we talked about, that we could just push some immediate value. The length couldn't be 1 byte because you are providing immediate value, but here the value would always be inside the register pair. Therefore the length of the instruction is 1 byte as the opcode. So push B has in hex the value of C5. Let's see how this would work out in the CPU and memory. So these are 4 operations that would be done for push B. We have the CPU here and our memory in here. Let's see, the value of B register is 0A and C register is 1B. You know that when we say 0A, it's actually the value of 0000 1010 is just for simplicity. We are showing it as 0A. Then 1B in the C register, the SP would have the value of 0015, meaning that it is currently pointing at this location, or this is currently on top of the stack. The PC register would have the value of DF04. Again, DF04 would be the value of 1101 and FF1111, 0000 and 0100. Every hexadecimal digit is 4 bits. And right now, well, we have, let's see that we actually didn't have any value. Like what we could do is this. What we could just represent this in a better way. Let's say in IR we have some other value from previous instruction. I just show it as 8x's. Now PC is pointing to the location DF04. This is DF04. We know what CPU does is that it is in an infinite loop, fetching whatever instruction is at the memory cell that PC is pointing to. PC is pointing to DF04. Therefore, the CPU would fetch the value of DF04, which is 11000101. So this value would be written inside the IR register. So as part of the decoding of this instruction, the value of PC would be incremented to DF05. Therefore, in the next cycle, the PC would fetch whatever instruction is at the DF05 memory cell. But all of these details, you already know how the CPU would fetch, decode, and execute an instruction. So right now, the CPU is in the process of decoding these 8 bits. What are these 8 bits? In hex, this is C5, which is the same thing as the push B. So the CPU needs to execute all of these operations to finish the execution of push B instruction. Let's see how this would be done. The first thing is that the CPU would decrement the value of SP to SP-1, right? So right now we have the value of 15 inside the SP register, which is 16 bits of length. So this would be 0014. You know, again, everything is in binary for simplification. We are just showing them in hex. So SP would be 0014, meaning that now the top of the stack is here. This value would be put on the address bus of the CPU that I haven't shown in here for simplicity. This value therefore would choose the 0014 memory cell. Right now this memory cell has been selected. You see, the exact timing diagrams would be explained later, but right now 0014 memory cell has been chosen. Next, B should go to whatever SP is pointing to, right? Meaning that B register here, the value of B register, these 8 bits, would be put on the data bus, and the control signals would be sent, causing the 0014 to have the value of 0A, or causing the writing of B register inside whatever memory cell has been selected in the memory, which is the value in the SP register, which is the 0014. Next operation is that SP should again be decremented one more time. So 14 would be now 13, the same operation. Now this value, now the 0013 would be put on the address bus. The memory cell of 13 would be chosen. whatever is in the C register, which is 1B, would go to the memory cell that SP has selected. So here we would have the value of 1B, and the push has been now completed. Therefore, whatever counter is there would be actually reset, and in the next cycle the CPU would fetch whatever instruction is at the memory cell of DF05, which would be something here. So this was the execution of push B. And if you notice, when we say we have BC register pair, it means this is higher byte and this is lower byte. It means that we have the value of 0A, 1B in hex. We said that higher byte should go to the higher address, lower byte should go to the lower address, right? So 0A is the higher byte. It has gone inside the 0014, which is higher than 0013, which has the lower byte of 1B. So this was the execution of push B. Let's talk about the other pushes as well. We have push D, push H, and push PSW. They are the same thing. Push D would be the DE. Instead of BC, it would be DE. No other difference. Then H would be the HL. And finally, PSW, the higher byte would be the A register, and lower byte would be the flags register. Now let's also talk about the steps that we took here in order for the push to get executed. The first thing was that the IR register, it was loaded with this value, which we call this one fetch machine cycle. So the first step was fetch. Then what were the other instructions? The first one, we said that SP was decremented, putting on the address bus, and a value from a register was put on the memory. We call this a step. We said from CPU to memory, we call this a step a read. So we just call, you see, before we just called it steps, then we called it machine cycles, and now I'm just giving you some hints on how these machine cycles are actually executed inside the CPU. Some value would be put on the address bus, some memory cell would be selected, some value would be put on the data bus, those and the control signals would be generated for the memory for those value to be written inside a memory cell. Now you might say, well, the addresses are 16 bits long and the data are also 8 bits, but we only have 16 bits of both address bus and data bus, and we talked about how 8 bits of these 16 wires are multiplexed between sending the addresses and data. So some of these control signals would tell those wires that I want you to act as address now and now act as the data. But one thing which is sure is that we never send the data sooner than the addresses. First, the address should be put on the address bus for a memory cell to be selected, and then we put the data. You see, we are not right now talking about these timing diagrams. We are talking about the steps needed for the completion of push instruction. I'm just giving you, making you, I guess, more ready for when we get to the timing diagrams, because I want you to feel the need, I guess. So this was the next step, which was a read, but then again, the SP was decremented one more time, put on the address bus, a memory cell was selected again, the value of another register was was written inside a memory cell. And sorry, I said this is read. Actually, this should be write, right? Because he said from CPU to memory is write, from memory to CPU is read. So currently we are writing from CPU to the memory. And then, well, another write finally would be done. So 3 machine cycles or 3 steps has been done. You see, we talked from the CPU perspective. That was just a mistake that I said R instead of the W. So these are steps or machine cycles. We say that it would take 3 machine cycles for the completion of push B or push any other register pair that we said we have 4 pushes. For the completion of any of these 4 push instructions, we need 3 machine cycles. Fetch, write, and write. One write for putting the value in from the higher order register which is B register in our example, and another write for the lower order register. Again, when we put the values from CPU to memory, it's right. When we are getting the values from memory to CPU, it would be read. So on the opposite of the push, you would have pop, which I'm going to explain in the next lecture.